Hello and welcome to video 10 of my programming the Nintendo Wii in C. So in this video I will introduce you to a little game I've made called Super Homer Brothers. Obviously it's based on the NES Mario Bros. So let's take a look at the game so you know what we are getting into. So the level is loosely based on the NES Mario Bros game. So it's kind of like the early sort of platformers which sort of come out for the PlayStation and the N64. If you think of like Crash Bandicoot, where it was kind of a platformer. Anyway, let's skip this level a moment so you can have a look at the next one. So you notice now we've switched to Luigi. This happened, there's 4 levels in total I've put in. So if you look around you can see we have a background here. This is a Skycube, and then we have a water effect here. This is a plane which has its UV coordinates scrolling. I will show you how we do that. So I'll go through all of the levels a moment quickly. Levels 1 and 4 share the same graphics. Same with 1 and 3 and 2 and 4. So you'll see there's if I jump past these a moment, we have 2 different Goomba types here. They track you, as you see. I will discuss that shortly.
That was too easy.
So let's complete this level. There we go. That's the game 1 there. So we got full mini game code there. So the next thing we will check out now is all of the models that I have used in this game here. So we will start with Luigi Homer here. Just like in the animations videos here, you'll see all of his limbs are set up ready for our simple animating here. This one doesn't look quite right. The main sort of model to use is the Luigi one. They're both the same. This is more of a sort of like testing one, if you like. And then we have our Goomba which is pretty much the same as the one in the animation video. And then we have a number of different level tiles here. So this is the standard blocks. In fact, what I'll do is I'll side by side what we've actually got here. So this is how the levels were sort of constructed. I basically downloaded these level maps here. I've got a grid enabled in here, 16 by 16 pixels, and this allows you to see clearly where the tiles actually lie on the actual level here, which this guy has exported here for us to view nicely. So all I did was I kind of went through these levels here and then plotted out a level map like this. So this one here is basically, if I split this into columns a moment, there we go. So these columns here, this is how the level data has been exported here. So the colors at the top here, each of these represents a tile type on here, each of these colors. So the floor here is actually this light magenta color there, and then the let's have a look. Let's side by side these a moment here. And then as you see, because this level here is obviously a flat 2D level, rather than have the level be one block wide, I decided to make it 3 blocks wide. But also decided that it might be good to have some blocks be 1 block wide, which is why these grey colours here, these represent 2 different types of bricks. The dark grey one there is a brick which is 1 block wide, and the light grey there is a block which is 3 tiles wide. So the brick setup is the brick styles here, so it's loosely based on these. And then you'll see we have some pipe types here. So the pipe sizes in here, they basically consist of like a top for the pipes, and then a bottom set of tiles for the bottom sections, which is, it's kind of similar what I've done here. So I have, because there's different heights of pipes, these are represented by the different green colours here. And then this dark magenta colour here, this is just like a padding colour, if you like. It doesn't actually represent anything in the game, it's just for when we look at the levels, we can see how many tiles wide or tall something will actually be. So if we look again here, this is one of the blocks in here. So if I bring this about here, scroll through the level here, you'll see these are the blocks here which are built into sort of like steps, if you like, in the game. These are represented by this brown colour here, And then if we scroll through here, you'll see we have the sort of steps as well here. Obviously, there's no reason for these to be filled in, as this is in 3D. You will not actually see these gaps here because of the way you'll be sort of viewing the levels. So each of these like pixels on this layout here will be substituted for one of these level blocks here. And then we have the brick tile here. So the block here, you'll see that its UV coordinates here have been scaled. So if we kind of look at that object there, so you'll see here that the UV coordinates on the x-axis are scaled by 3, and this is because we can basically use this 1x1 cube to represent 3 tiles wide, and then this model is used for both the 3 brick wide blocks using the brick texture, and also the block images here. So you have like the blocks there, the bricks there, but in our levels the bricks can be either one tile wide or 3 tiles wide. If it's 1 tile wide, then I sort of center it in the sort of X region of travel. So again, these are the levels are loosely based off of these here. Obviously some of this doesn't fit. I didn't bother having any mystery blocks or any of that sort of stuff. If you look at the actual level for the standard NES game here, you'll see that there's not really anything visible to sort of collect here. You kind of in this game you kind of have to obviously hit the blocks to sort of score hidden coins. Obviously that wouldn't sort of fit with this game here. So what we have, the yellow pixels here represent like donuts. The red colors here represent where the enemies are, and then the purple the magenta one here is just a spacer, like I said. The blue represents the level exit. So if we scroll to the end here, there's our exit there. And then if we come in here, our exit is actually made of the flag base and the flag pole. The model is obviously, the models were reused from the N64 and the 3DS, hence the low polygons for them. These are obviously moved together to sort of construct a final sort of flagpole on top of everything. And then this is our floor cube here. The UVs are scaled 2x2 on here. And then we have our pipes. So what I did is if we come in here, wherever there is like a, so you see here, this is like a 2 tiles high, so you would have one pipe section here and then one pipe top. Which would sit on the top like that. Obviously in the actual game these are scaled appropriately. One thing to note with these is where the origins are. So you'll see the little yellow dot there is the origin of this cube top here. So if we rotate it, you'll see it rotates around that there. But also note, if we come to the side view here, you'll see its origin is aligned to the top of it here. And the reason for that is for easiness in working out how things collide with these models, which I'll get more into in the collision part of the video. And then we have our sort of sky cube here, which is the sort of background. So one thing to note with this, when you sort of create like a sky cube, what you have to do is flip the normals. So you see here the faces are all red, and that's because the normals are facing the opposite way. If I scroll, okay, I can. If I look at it from, if you look from below here, everything's blue, which is what we want models to be, and this is because the faces all face inwards. Because obviously we're not viewing this from outside. We're viewing it from the inside. So all of the faces, the normals are inverted. I'll show you another model here. The donut, for example, you'll see that its faces are all blue here. That means its normals are calculated from outside of it. Which is correct for all models you view normally. However, because this is a sky and we're going to be actually inside of it, you have to flip the normals so that the blue is the opposite way around. Normals basically inform the GPU what way the faces are actually facing. So if we wanted to flip these around the opposite way, what you would do is go into mesh and then normals, and then you would calculate outside, and you'll see it's changed to blue. However, we want these in the inside because this is a sky box. So I just wanted to point that out to you. And then lastly we have our water. So this is the wrong texture for this actually. Let's find the correct texture here. So it's something like this one here. In fact, I'll just navigate to the actual project in here. This will do. So you see that the UVs are actually scaled by 4. Not sure if this is the X and Y UVs are scaled by 2. If I bring this up here, you'll see that it's scaled 2 by 2. This is probably not a good texture to use actually, as it doesn't look like it's properly symmetrical. So that's not a good example. Let's find the right. Let's find the correct images. I'm not sure where I've actually put them. These don't seem to be in any real order here. Here we go. There we go. You can actually see this texture is properly mirrored on the X and Y axis here. So we have the water here. The reason why it's the UVs have to be scaled by 2 is because I've created like a function which takes in our mesh data and you supply it with a UV offset on the UVX and the UVY coordinates. So a number between 0 and 1. And then every so often what you do is you update those UV coordinates and then it regenerates that mesh with the new UV offsets. And what that does is it creates like a scroll across the surface of the model. So it'd be good for like a water or sort of like lava or a floor which appears to have some sort of scrolling material. So those are all the models in the game. I will obviously supply you with this Blender file so you to have a play around. So as I said, these levels here, so one thing to bear in mind is the sizes of this level and then the tile types here. So you basically, if you want to make your own levels, you can reuse all of the sort of tile types I've created, or even add your own and then just add like another sort of color key to whatever tiles you're creating, and then you can just plot them wherever in the levels. These are obviously tailored to the sizes set out in the level manager, which I'll come back to all of this in a bit anyway. So let's jump into all of this here now. So the topics I'll cover today: scroll and large levels, which I've obviously just sort of started talking about, platform collisions. So in this game, as we are moving in all 3 dimensions now, rather than using collision rectangles, we are now using collision cubes. Obviously, if you're just moving around in 2 planes or 2 dimensions in your game, then you can just use rectangles because obviously it's easier. But if you are moving in all 3 dimensions, then cubes are probably the most simplest way to go. I'll then go into how the actor jumping and falling works and the various collision functions I have. Then I'll talk about the simple enemy movements in the game. I'll then briefly touch on lighting. So this game uses just one light, which is permanently above the player, and I think that works fine. And then obviously there's the Skycube and the water effect, which I was just talking about how it works. I'll show you the functions for that. The Skycube is it's just a case of kind of centering it over the player, really. Same with the water plane. You kind of they kind of like follow the player throughout the world. And then another quick note, obviously I won't be discussing anything that I've previously covered. This is to keep the video as short as possible. I've no idea how long this video is going to take, so let's get on with it. So as I was showing you here, basically we're getting an image of a level here, and then in this case we've identified the size of the tiles in the level. They are 16 by 16 pixels in size. So what this allows us to do now is to create a level map with one pixel representing one tile. So one thing you'll need to know is how wide the levels are and how tall. So if you have a look at this here, so in the rightmost two numbers, those are actually tiles. So you'll see that's tile 0, that's tile 1, tile 2, and that's tile 14. So it's 15 tiles high is the normal height of these levels and tiles. And if we come to the end here, in this case I think it's 224 tiles wide. Obviously I'm not drawing the house here, so I kind of tuck mine to I think 208 tiles wide. Yeah, so the dimensions there, you'll see 208 by 16 there, that's the size. So the levels, so exclude this here. This is obviously a kind of color key for the level itself. So the level's obviously 208 by 15 wide to kind of loosely reflect these here. Obviously I didn't create any bonus regions here. So you kind of get the gist how this sort of works here. And the same with this here. So one thing to note, in fact I'll talk a bit more and then I'll come back to this here to explain when we export this, or rather when we import this into DS to tile, which I would advise you to use. The tile sizes will be 1 pixel wide by 15 high. And the reason for that is obviously this is a horizontal scroller. So if we look at this, if you look at this image here, you'll see I've put these white blocks intermittently throughout the level. What these white blocks actually indicate is the level broken up into the width of tiles which are viewable on the screen on the NES. So if I move this rectangle here, so if you imagine this here is the viewport or the scroll window, obviously all you can see is a certain amount of tiles at a time. So as this moves, obviously we lose tiles at the back end here. We can't see these, and we've obviously copied a new strip or a column of tiles. So on a horizontal scroller, you kind of need to arrange the level data when you export it from an image, or rather convert it from an image into tiles. Ideally, you arrange them in columns like so, which is indicated here. So this would be like column 0 here, this would be column 1 here. And the reason for that is obviously you only need to bring in or scroll on one column at a time from your level. So as you sort of scroll along, you copy one set of one column of data to sort of scroll on to your level. Hopefully that kind of makes sense to you. So in our game, the sort of like scrolling is kind of similar to a sideways scroller, except instead of in the original game here, everything scrolls on the x-axis. What we've actually done is we've substituted the x-axis for the z or z axis here. So as a result, everything will kind of be scrolling towards us. But rather than have it like a one tile wide, like I said, I implemented it so everything's kind of like 3 tiles wide. So this is kind of like a distance now, if you like. We're seeing a distance from like Mario's perspective, if you like. That's kind of how you're viewing the level now. So rather than it be like 1 block wide, I've kind of made it 3 blocks wide, but obviously you can increase things as you see fit. All you need to do is add another sort of a pixel color, and then that pixel color would be a new sort of level block. So what we sort of have here is we sort of have like an imaginary sort of viewport for our game, which is roughly the same sort of size as the NES viewport of 16 tiles wide by 15 tiles high. So what we are doing is we kind of have like a list in the game of level objects, and we add objects to that list when the right side of the window scrolls over them or to them, if you like. And then everything that drops out the back side here, once their leftmost corner is outside of the viewport, we then release them or destroy them, if you like, from the object list, which is kind of exactly what you kind of do in the 2D games from this era. When you sort of scroll, as soon as something scrolls onto the viewport, you would also need to have like another sort of rectangle to know that these tiles or blocks are now viewable in the world. And then once they become viewable in the world, that's when you kind of give these objects like properties in the world, because obviously you need to be able to sort of collide with them and interact with them. But they only have these physical properties associated to them while they're actually in the viewport or scroll window. As soon as they pop out the other side of it, you take those properties from them again, because those properties, they obviously take up computing power. So you only have a limited supply of them, which are given to physically viewable objects in the world, like the player, the enemies, or the actual collidable, interactable objects. Hopefully that kind of makes some sense to you here. And you see here, so this is the way that we're doing things here. Obviously, if we had a vertically scrolling game, then instead of ordering your tiles in a column here, you would position them in a row here, because you would be sort of scrolling up or down. So instead of having them come in on the sort of sides here, they would scroll in top and then move down. That's how that kind of works. So as I said here, I've switched the X and the Z axis here. And then the viewport obviously clips everything around the player. So what's actually happening is the viewport would be centered around the player. So as the player moves, the world kind of moves with the player, and then new objects enter the world in front of the player, and they're obviously removed from the viewable world behind the player. So I was sort of saying the depth is sort of handled by the tile types here. So if I jump into the actual level manager here, as is always the case here, so these are the tile types, and these all correspond to these here. This color key here basically corresponds, each of the numbers here corresponds to this list of enumerations of level tile types. So if you add a new pixel color here to represent some new actor, model, or whatever, then you just make sure that you add a new enumeration here, so that you can obviously pick it up in the code. And then here I was just saying that I obviously how I actually sort of converted the levels here, and you can kind of, if I navigate to my NES graphics folder here, so you'll see there's another one here for one of the underworld levels here, which is kind of loosely what level 2 is kind of based off of. And again, the you've got the sort of bricked out bit here. So if I open up the second level in here, it was kind of loosely based off of this, but then I sort of changed it even more, as sometimes what you'll find is some tile types, if you sort of convert from a 2D level to a 3D, kind of don't make any sense. Also, the more things you have above you, the more frustrating it potentially becomes when playing it in 3D, because obviously you don't know that they're above you as you're not always looking up. So when a Goomba sort of comes along, you jump up, you hit a platform above you, and then fall onto the Goomba, which sometimes happens in this game as well. So what I was trying to do is to try and make it so that's not always the case. So it could be that you raise some of the platforms up a bit more, which is kind of what I was doing here. You'll see that some of this is very similar here. For example, I kind of raised these bits up a bit more, and then it loosely kind of follows this here, the sort of rules here. I think you get the idea. So what I'll quickly do in a minute is just to show you importing a new level, is to quickly change this one here. In fact, it's easier just to copy that whole thing, isn't it? Put that one there, and then save this one here. And then the way to sort of the way that I've sort of been doing that is with the DS to tile program here. So always make sure you put it to 256 color bitmap mode here, and then it's 1 tile by 15. That's the sort of size of 1 tile here, so that kind of corresponds. That will make sure that when this is exported, it will be exported a column at a time. Let's get back to here, and you'll see if I side by side these, we have our test level here. Just drag and drop that across, and then we'll save that one there. So you should get 208 tiles. And then if you navigate to the data in the actual game here, what we'll do is we will just comment out all of this. And we'll come back up to the top here. Now we need to navigate to the DS to tile folder where we saved the level. And then you'll see that it's created like one long list. And that's obviously because it's 1 pixel wide. So I just cut and pasted that straight out of there. So what we should be able to do now, save it and then rebuild. And then if we reboot that up, So if we look around there, so you can zoom the camera out slightly as well.
Get out of my way, jerk-ass!
And then also notice once you move away and you come back that the world has disappeared behind you. And then there's the other problem of not being able to see what's above you. That's one of the pains here. But anyway, that's an example of how easy it is to update the levels for this. I'll now delete this out here. And then we'll uncomment this out. So I think that sort of that gives you a good idea there how the levels were created. So the scrolling, the 2D game was obviously split into tiles, like I said. The tile should be obviously arranged in columns. I think I've probably already sort of talked about all of this here. Bring this over here a moment. So I'll try and touch on some of this stuff in here now. So there's lots of different defines in the level manager here, which I will advise you to sort of have a play around and a look at. So standard tiles, I've given them like a height, a width and a depth. And then there's obviously wide tiles, which are these. These are obviously 3 times the width of a standard tile. Again, you can put as many wide as you like, but you would obviously have to create like new sort of tile types for them. So that means you would need a new sort of enumeration for them in here. You could have like a brick wide 5 or 7 or 9. I'd say it's best to go up in odd numbers width wise so that you can have like things centered nicely. Some of this you might have to sort of figure out for yourself by playing around with. I might not be able to actually describe it in such a way that you can understand, I suppose. And then I have like lots of half heights and half widths and half depths, as you kind of need to know some of these for working out where to sort of position the models in respect to the world tile locations. This is dependent on the origin of the actual models themselves, which I'll get more into in a moment. And then we have some defines for the viewport here. And then down here there is actually, so the viewport itself is actually a rectangle. There we go, the level manager scroll window. So this, the reason why this can be a rectangle is because this isn't actually interested in any depth. So what I can do now is if I change the pixel grid, sorry, not pixel grid, grid settings here. So this is how wide the scroll window is here. And this will be centered on the player in the x-axis here. So this is strictly rectangular in nature here because obviously the world tiles are only like a couple wide. It's only interested in the depth values. So the scroll window is basically the 3D viewport. Once we move one tile's depth, we then basically do another. We then need to do like a read of the level data on the rightmost side to then pick up the new tiles to add to the level list. So there is a define for that as well. Where is it? I think it's this one here. So some of these are for the viewport in tiles. There's one for the level width in tiles here. Another one here as well. Some of these defines will be for actually limiting the scroll window itself. Obviously we don't want to try and read data from outside of the array for each level. And then these are concerned with where the sort of margins should be, as in the left hand margin here and the right hand margin, which will actually be like one tile in front here. And the reason why it's the right margin will be like one tile in front is because we always kind of want to have something just outside here to scroll into view. And there's some defines here for the skybox, the water scroll time, and then each object has a level object associated with it. This is primarily for the background objects. And then there's like a separate one here for the exit object, which obviously will only come to life when it actually is picked up in the viewport for the first time. So the first time it's sort of found when you're scrolling along is when it will sort of come to life. So if I just jump into the LevelManager code itself. There we go, this is it here. So this here is the so this size is just a kind of size that I sort of just plucked out the air, but it's loosely related to the amount of pixels in this area here. So I think initially the way I sort of got to that value was I sort of estimated, well, the initially it was 20 by 15 in size, this rectangle here, and then the way I sort of looked at it was, well, 20 by 15 is 300. There's never going to be, so you can sort of work it out, the width times the height. So initially it was 20 times 15, 300. And if you times that by, say, 0.75, I think that's how I did it. Or it might have been 0.8. Round about there. So there's never going to be, or there should never be, too many level objects existing at any one time. There's like a purge function in here which we kind of we sort of call after we sort of scroll. So you're not sort of purging every one unit you've sort of scrolled. You're kind of waiting until your scroll has moved like 8 units. One thing to bear in mind is, because this is 3D, but we're working in, it's not 2D, these aren't actually pixels, they're obviously units. I'm kind of loosely kind of relating them to pixels to some degree. So what these level objects basically represent is kind of like a cache, a pool, if you like. And when these objects here are inside this viewport, each one of them obviously has all of these properties here. Obviously, given them all these properties here, some of these will obviously relate to them actually being drawn, but then others, for example, the cube object here, this is for collisions. So once all of these things actually have a property and they're viewable, we should be able to sort of collide with them in some fashion. So you see we have a list of them here. And then one thing to note in here is there is a boolean to say whether it's alive or not. And that's because when you sort of scroll along, you just want to be able to sort of add new level objects as and when they're needed. But what that means is obviously the ID, or where they are in this list, kind of becomes irrelevant. So when you add new ones, you kind of have to iterate over the whole list again from the very beginning to sort of try and find new ones which are obviously not alive, and then turn them into being alive again, and then give them new properties for whichever new tile you sort of add. And then the all the ones which are alive are obviously the ones which get drawn each update. So let's go into how the scrolling sort of works here. So like I said, the rectangle gets centered on the player, the scroll window, and what this takes is the player's Z and Y position. So you'll see here there is a center camera function here. So let's go over all of this now here. So what we'll do is bring up both of these here. So in the left hand window here we have this sort of main game here. There's a function which is draw scene, and then it's not this one here, this is for the actual 3D camera to follow the player. Where is it? I think it might be picked up in the actual player here actually. Where is it? Is it in here or the game? Might be in the play code actually. Here we go. So this is the game state play function here. And then you'll see after the player update function, there is the LevelManager center camera function here. And this is what kind of triggers the whole sort of scrolling process here. So we pass in the player's vector3, and then this function here, there's a boolean to say whether it's the start of the level or not. The reason why there's like a start of the level or not is because obviously once you start a new game, so when you start a new level, you obviously have to then go through and obviously add all of these columns one by one until you kind of fill the whole sort of viewport here, going from 0 to the max sort of length here. That's why there's a boolean there. So obviously if it's the start of a level, we obviously need to go through the whole width of the viewport, whereas if it's just a normal sort of game, we obviously would only want to do one column. So what this does here is we have like an old camera position. So what we need to do is we need to work out the distance the player has travelled in units. So you'll see we have a left hand margin and a right hand margin. The left hand margin is basically the distance behind the player that the left hand margin should be, and in this case what it actually is it's the level map width divided by 2. So it kind of centers the player loosely. So you'll see we're working on the z-axis here, so we basically subtract the left-hand margin value from the player's z coordinate, store it in LX for the left X position in 2D. And then you'll see what we actually do is we prevent this left-hand margin here from going behind the actual old scroll X position. So this value here, this is kind of set up first off when we initialize a level. Let's find that code here. What I'll do is I'll start minimizing stuff a moment. So when a new level is started, the camera is always at 0. So if I come back to here, you'll see that everything starts from the left hand side here. So the camera's left hand side would be 0 here. We're obviously only interested in recording the old X position. And then we have like a temporary variable in here called old camera position here, which refers to the old scroll X. So we make sure that we can't sort of go back before that. The reason for that is because if we go back, then we obviously have to start adding tiles from the left hand side and then removing tiles from the right hand side, which I didn't want to do. So I sort of have it so that the world disappears behind you. And then we also want to make sure that the position cannot go below 0. So we clamp that here as well. And then what we need to do is we need to work out where the right hand side is in relation to the left hand side. And then you'll see the right hand side just adds the level map width and pixels, although obviously it's units, not pixels, which is just the depth times the width in tiles. Which is here. And then what we do is we make sure that we've not gone past the actual levels width. So what we do here, so the level width in tiles here is this here basically. So what we're doing is we make sure that the right hand side is inside of the actual level there. Normally this right hand side should always be back like a full screen or a full sort of window width. So as we're sort of scrolling along here, we kind of want it so that we don't go past a sort of like a whole width here, if you like. So we don't sort of go outside of this area here. This is where we'll sort of get to. So we can't sort of go past that, if you like. So once we've set up the clipping, we then re-estimate the left hand side from the right hand side. We then plug the new left hand side into the scroll window's X coordinate. And then at the start here we set the scroll to false, because we obviously have to figure that out ourselves. And then if this is false, then we need to work out if we've sort of scrolled or not here. So all we do is we convert the floats into integers to make it easier. And then we work out the difference from the old camera position and the new left hand side of the scroll window here. So the difference is basically the left hand side minus the the camera position minus the left hand side here. If it's less than or equal to a tile depth, then that's for like scrolling left, which we do nothing with. However, if we've scrolled greater than, so if the difference is greater than or equal to a positive tile depth, then we have sort of scrolled. So we're kind of doing the same sort of thing again here. This is the main one that we're interested in here, so we're not interested in the sign, we're interested in that this has been achieved here. And then this here is where the sort of scroll occurs here. And then after this, it will then update the old scroll X position here. So if we jump into this part here, this is where we start reading the level data here. So you see that it says scrolled and left, and that's obviously because everything is obviously moving to the left here. So if we haven't scrolled the depth of a tile, then we will return here. And then this just works out where the starting X needs to be in the level data. So we're working out here where the if I come in here, where the sort of column needs to be here to copy from. So if I convert that back to columns here, what we're doing is we're kind of getting the working out the sort of right hand side of our sort of scroll window. In this part here, I probably should have removed this here actually. So this is the bit we're interested in here. This works out the X position of the right hand border basically. We then basically subtract 1 from that, because usually that's like a tile ahead of where we sort of want to copy from. If this is greater than the level width in pixels, we return obviously this, and then what we now do is we convert the X coordinate in pixels to the level position in tiles, and this is so that we can set up where we need to sort of copy from for the right hand like column. And then first off, before we do anything else, we call the object call function here. So all this will do is this will work out if an object is basically outside of the viewport. So this is the left hand side minus the depth of a tile. This is the right hand side, and what we do is we start at 0 and we basically iterate over the whole of our sort of level data array. But we're only sort of doing this until we find the exact sort of count aligns up with how many are actually alive, so we can kind of not need to iterate over the whole list, only until we find the amount that is actually alive. And then if one of these is outside, we literally just switch its boolean to false to remove it. We then subtract 1 from the actual level objects. So you'll see at the start here we record the old count as being the current count before we've removed them. And then we add to the objects removed there as well. So that should free up a load of objects first, and then what we do is, using the X start coordinate we've just worked out, we can then point our unsigned char pointer at whichever the current level data is, and then we just need to iterate over 1 column, which is what this is doing here. And then we basically read the various level data here, and then we compare that against the tile types we've defined here. And then there's just one sort of global add function for the various background tiles, and you'll see here if we register that there's a Goomba there, then we call the baddie manager add function with the Y position, and with regards to the Goomba, the Z position, where it will start at. And that's basically the scroll there. Hopefully it kind of makes sense. Again, play around with this stuff to see what happens when you sort of tweak values here. Pretty sure I probably don't really need this in here, to be honest. The left hand side, everything is kind of just working with the right hand side. This is kind of in there because initially I was going to have it that you could sort of scroll backwards and forwards, but then it was just an extra hassle. To work out having to sort of add from the sort of left hand side. So that sort of covers the sort of scrolling stuff here. This is probably the most confusing part here, is this stuff here, trying to figure out what's actually going on. Basically it's just this here. As you move along, if you've moved one width of a tile, or depth of a tile in our case, then you need to just add new tiles from your level data array. That's kind of what's happening. So let's see what we need to talk about now. Platformer collisions. I'll jump past all of this now, so look at that. Let's fix that a moment. No, not that one. There we go. So as we are now working in 3 dimensions in our game, in fact, let's side by side things again here a moment. So this is our new collision type here. As we're working in 3D now, we're not using, or rather, as we are traveling in 3 dimensions now, we use the cube F object, as I'm stating here, and then the old sort of rectangle collision looks like this, where we're basically just checking to see whether the X and Y coordinates of one rectangle fit within the range of another. So when it comes to the cube collision, it's basically the same, except what we have now is we have a Z coordinate as well to deal with. So you see here it's checking the X against the X of another. Make sure that X1 or the cube 1's X coordinate fits within the area of cube 2. Then the same with the Z coordinate there in the Z sort of area of cube 2, and the same with the Y there. Nothing special there. However, it's best to sort of stick to sort of cubes, as they are easy things to work with. The main thing you kind of need to bear in mind is alignment of your 3D cube over your models. This is where we kind of need to jump back into Blender again quickly. And the reason for that is if we look at loads of these different objects here, need to bear in mind where the origins of these are. So lots of these are the bottom near side. However, when it comes to objects that need to rotate, generally I tend to try and go for the bottom of the object in the center of it. And that corresponds to the actor as well. The key point is where the actor's centered. So here, the whichever sort of if you add a bounding cube, this would need to be sort of centered over, making sure that it kind of fits exactly over the actor. And then the pipes. One thing to note here is they are below the starting points. So their origin is there, so you need to make sure that the cubes themselves, the collision cubes, fit over these objects as you expect them. Otherwise the collisions won't sort of work right. So the level manager itself has a few different collision functions here. And normally all you do is you pass the collision cube of an actor in there. And then the level manager will check the list of level objects. And then if it finds one which is alive, which corresponds to the type we need to check against, then it works out the collisions in here and then just returns a boolean normally. So basically in here I'm basically saying same as what I was just saying there. So the key thing to look at in here is the creation functions for these background models. So the add object here, this not only creates the physical properties for each level object, but it also creates the collision box for them as well. And there's a number of different functions in here for the cubes here. You see there's one here for center on a vector 3, which takes a boolean here which says whether it should do the same for the height. So that's the y-axis there. Most of the times I would pass false to that. As lots of the objects, their origins are at the bottom of them, but not all of them. So again, you kind of need to know your models when it comes to working out the collision cubes here. So most of the time here, you'll see these scale sizes here. So the add object function, it takes in the tiles X and Y position from the level data and the object type. Because obviously the level data obviously only has an X and a Y here. And then you'll see in here that the tile X coordinate here is put into the Z coordinate in here. One thing to note in here is all of these positions for the Z coordinate are positive at the start here, but when we draw them, we flip them so they are negative. As is always the case when working with OpenGL, everything needs to be drawn down the negative Z axis. And then depending on the model type, depends on the scale size of the collision cube. So some of these, for example, the sort of floors, the bricks and whatever, the collision cubes themselves will align perfectly to those as they are. Another thing to note as well is how the Y coordinate is calculated. So when we're looking at the world here, 0 is actually down here, and the height of the level is up here. So what that means is when we read these columns, to convert them to the world, we have to start at the top of the world, if you like, and then work our way down in steps of tiles, as this is 0 here, which is what this is kind of doing here. So the variable here, map ceiling, is actually the height of the map minus 1 times the tile height. And then all we need to do is to convert the tile position is we times that by a tile size and then subtract it from the ceiling height, and then that just enables us to sort of come down from the top here. That's how these positions are sort of set out here. And then some of these look exactly the same. The sort of creation process here, where there's the floor and the wide brick is basically exactly the same. And then there's also a collision type for these we set in here as well. And you see there's some different mesh types. The wide brick is obviously using the same as the block, like I said earlier. All of the sort of rectangular sort of ones are pretty much straightforward. Where it gets a bit tricky is the pipes. So if I come back to the level here, so you'll see we have the three pipe types. We have the tallest, the middle one, and the small one. So we have the pipe height of 2, the pipe height of 3, and the pipe height of 4. So you can see here 2, 3, and 4. Like I said, one of these, the topmost one, has to be the top of the pipe. And then this kind of just works out all of this here for the pipes. So there's like another variable here to work out the sort of collision position for the pipe. As just shown here with the pipes, you see that the top position there is the origin for the pipe. So our collision cube, if I just add in another cube here, this kind of let's scale that 1. What we need to do with this is we have to align it so it kind of fits with this. However, the collision cubes themselves, their origins are always at the bottom near, so you have to kind of move it up a tile, or sorry, move it like down a tile from the origin here so that it fits with this, which is what's sort of happening with the pipes here. Which is what you need to bear in mind here. So you'll see that this moves down by 3 here, moves down by 2 there. Let's close that and not save it. So I don't want to be dragging code around with a mouse, that's not what I'm aiming for here. So enough said about these. This is just something to bear in mind when you're looking at these. And then the donut uses the center on vec 3 position for the donut. And then the flagpole is put in here as well, which is kind of treated kind of separately when we come to draw that. So the key takeaway with the add object is it adds the collision part as well, the collision cube. The tricky part is making sure that the collision cube is aligned perfectly on your model, which comes down to you needing to know your models that you use in the game. sometimes it's handy to have the ability to draw your collision cubes, which is why there is, I believe there's an additional cube in here. Yeah, there's one for left bottom and one for center bottom. So depending on how your sort of cube is aligned, it might be worth drawing them if you're sort of having issues figuring out why things aren't working as expected, which is what I sometimes have to do. So I'll talk about the actual collisions with the cubes now. So let's have a look here. Match up the functions here. So we have the on platform, the hit wall, the hit object, and the hit donut. Most simplest is probably going to be the hit donut. So we'll look at that one first. So all we're doing here is iterating over all of the level objects. We check to see whether our temporary object is a collision type donut. So adding these collision types in here, this also can speed up working out which object type you are actually working with. So in here, this is obviously just checking one unsigned int against another first for speed. So when we added the objects, where are we? So you see here, where is it? Donut. So our mesh is obviously a donut there. And then the collision type is passed into the object type ID there. This just allows us a quick way to know which type we are working with. You see there's another one here for the exit type as well. So back to here. So now we know that the object here is a donut. We then check to see whether the passed in collision cube overlaps with this object's collision cube. If it does, then we can return true. We also set this object to be false. This means we have one less object and we have removed one object. And it's as simple as that. So the next one is hit wall. This is straightforward again as well. It's doing exactly the same, except all we're interested in here is if the collision type is an obstacle. Normally this function here, you would just call it when you're sort of moving along, not jumping or anything. And this is for, you're not interested whether it's a platform or not. This would just be checking whether you've sort of collided with something in front of you. And then the next one would be the hit object and jumping. Now this one is a bit more involved, and the reason for that is we need to check around the sort of perimeter of whichever object this is. Normally in this game the only object which would be jumping would be the player, as I haven't implemented anything for the enemies to actually do any jumping. So again, we work out the type, and then what we are working out is the half height of the object we are colliding with, and that is so we can sort of tell which direction we are kind of hitting it, if you like. So you can, if you are sort of hitting it from below, or whether you're hitting it from above. So we work out two different types here. So we work out what the top of it is just by taking our object collision box Y position and then adding its size to that. So this gives us the top of it, and then this gives us the half height of it, if you like. So if our character is jumping, what we do is we work out whether the collision box passed in is greater than or equal to the position of our temporary object here plus its half height. So if that is the case, then we need to sort of position our character on top of that. I kind of need to sort of bring this up here. So basically, I'll copy this, move that here. So I'll scale this one down a moment. And then basically the move that one. I don't think I'm going to be able to explain this properly here. So basically, if this cube here hits our other one here, what we need to check for, so the origin, this one, if you imagine it's at the bottom here, and the origin in this one is at the bottom as well. So this is the half size of that one. So if we hit it below that half, then we should fall out from it. If we hit it above that, then we should be positioned on top of it. That's what we're sort of checking for here. So if our Y position, which is at the bottom of that cube, which I just shown you, is above the half height of the one we are hitting, then we return to say we've hit a platform, which would then mean we need to well, you'll see in here we basically amend the passed in collision cube in here to be the top here, so it instantly jumps above the top of it. Otherwise it returns that we've hit an obstacle. You could also pass in the you could amend the cube again to be directly aligned below this one as well, I suppose, but I didn't do that here. And then there's also another one in here as well where we check to see if it's an exit. If it is, then we ain't going to bother changing the position or anything. We'll just return that it's an exit. Otherwise, it returns an empty collision type. So you'll see that this also says what collision object we've hit. And then the final one is hit platform. And this kind of does exactly the same as the hit object one here, except it will only return true or false. And then it will automatically sort of adjust as it needs to here. So there is a value here, platform Y adjust. So I'll come back to that in a moment here. So when it comes to actors and the that platform function there, what I'm kind of doing is when you pass in the collision cube here, you move it down a bit. And that's to ensure that you get a good sort of collision between one collision cube and another. Obviously the floor here, it will have a collision cube sort of totally over one cube tile here. And then if you do get a good collision here, then you know that you've hit the platform, then you would return true, and then you would obviously adjust the position back to being above the platform, which is what this is sort of showing visually here. And then in code, what it's doing here is let's show the platform adjust code moment here. Where are you? There we go. So like I said here, in order to get the player to collide correctly, you're basically subtracting 2 from the player's Y position. That's what this is doing here. So it moves the actor down like 2 units just to make sure that there is like a good collision there. If they do sort of interact, then it sort of does the same sort of check here. So the ceiling here is the collision this is basically we take the top of the collision object here, and then we work out whether the player's Y position is less than that. If it is, we reposition the passed in collision box. It's Y position to the ceiling here, and then we return true to say that we've hit a platform. Obviously there's no need, because we've updated this pointer inside here, we've adjusted from it here. At the end here, we obviously need to add that back on before we return false. So those are the collision functions in here. So now I think the player jumping and falling code. So one of the things I implemented in this game here is a variable jump height. So the longer you sort of hold down your jump button, the higher you will jump up to a maximum height. And this requires sort of a few variables to sort of hold when the jump sort of started, when the if the jump button is held down, and then we also need like a player state variable as well. So let's get into the player now. So the key stuff I'm going to focus on in here is the jumping code. Again, to figure out how all of this works, you'll have to sort of deep dive into the code here. So before we can sort of understand what's going on here, these are some sizes for the player. This is for the collision object size for the player. There's a maximum speed, and then there is some sort of like friction and acceleration added for the player. So he has normal sort of acceleration, there's like a force speed as well, and there is a jump acceleration, and then there's also like a gravity I've sort of set up as well. Play around with all these things to get like a decent feel for them. So one of the key things to understand is the states of some of these entities, which are in the utilities header here. So the entities refers to the player or the baddies basically. So they can either be dead, dying, idle, walking, on the ground, falling or jumping. And these states, they not only help with the actor's movement, but obviously they also play a role in what sort of animation should be playing as well. Again, the animations, I obviously talked about that in the previous video, so I won't actually be touching in that here, as it's exactly the same sort of setup. So the jumping of the player. So the player update function here, you pass in a combined set of flags, which basically where are they? They're in this one here, I believe. So you'll see here we have a number of like action flags here. So there is forward, backwards, turn right, left, jump, straight, zoom in and out. All of these here basically can all be combined into one variable, which would be passed in for the update function here. And then, where are we? Let's go to here. So first thing we do is we center the player's collision cube on their position. And then there's a few things here for jumping here. So there is a boolean here to say whether the jump button is held. So if you press jump, it says here the Boolean jump held is set to true, and then what it does is it checks to see whether the player is already jumping or if the player is falling. If both of these are false, then that means you can jump, because obviously here we're not allowing you to jump if you're falling, and if you are already jumping, then you cannot jump again on top of that. So this sets the stage here. There are some different booleans in the player here. So what actually happens in here is there is a jump held counter. So when you hold down the jump button, the jump held counter then starts incrementing. There's also a jump counter itself and a jump limit, which I'll get into shortly to try and explain these. So at the start of a jump, you see the jumping is set to true, on ground is set to false, falling is set to false, and then the jump speed here is set to the player's jump speed. At the start here, there's also a maximum as well. And then we have a jump counter and a jump limit. And the reason for that is when you sort of hold down your button, that obviously it will increase the limit. And it's the limit which is what sort of handles this sort of jump, really. Depending on how many times you hold that down, depends on how many times the whole sort of jumping loop will occur. And then in here, this just kind of sets this up here. And then as you'll see here in the sort of jump update bit there is a limit here. And then obviously depending on the limit here depends on the jump counter. So this just sort of sets up the jumping starting, if you like, and sort of carrying on. And then the actual jump bit here is where all of the sort of adding of the speed and everything occurs here. So after you've started, it calls the jump update to sort of decrement the sort of counts or whatever. So you see here the jump counter is updated in here. While it's below the jump limit, jumping is sort of fine. However, once the jump counter reaches the jump limit, then the jumping is turned off. And the actual sort of maths bit for all of that is all in here. So you'll see here we move the player's position by the jump speed. We then center the collision cube above them, check to see whether the players hit something using the hit object function there. So here this basically determines whether we've jumped underneath into an object or whether we are sort of jumping and we manage to sort of collide with a platform, in which case we will sort of align ourselves to directly above it and then switch off the jumping. Otherwise if we jump up into an object, then obviously we bump our head, so we play the bounce sound effect, the dull sound effect, and then we set fallen to true, jump into false, and then we have to update our collision cube afterwards. That's pretty much the jumping stuff then. And then the fallen code, it's just a case of keep sort of checking what the player's actually doing. If he moves, then you need to check to see whether he's hit an object. Nothing sort of special here. Loads of this was sort of like trial and error to sort of get it sort of going. If the player isn't jumping, then you kind of constantly have to see whether he's on a platform or not. That's kind of the way these things go. If they're not on a platform, then obviously they're falling. Otherwise, if they are, you kind of have to make sure you switch off the fallen code and put them on a platform. Again, check out most of the code to see how I've sort of done that here. Isn't really anything too sort of special in there. Lots of the times with the jumping and falling, it's a case of trying to figure out where to do the sort of correct collision sort of checking. The jumping itself, the variable height jump, again you'll need to sort of play around with the counter values to figure out how high you want the player to sort of jump. Where are the counters here? I think they're all set up in the initialize function anyway. Yeah, here we go. Basically, like I said, the counters are what sort of control the jump. There's a limit to how high you can jump, which is actually based on the counter limit here. So let's go over the enemy movement now. This is fairly straightforward. Once the baddies come alive, what happens is there's a function to get the angle between one and another. And all what happens is you basically take the player's position and the baddie's position, feed it to the get angle 2df function, which is in here. Where is it? And then this just works out the angle between one and another. So in this case, we've this is sort of configured so it's taken the X and the Z, and what it's actually passing back is the Y angle between them both, the yaw. But as I've said here, you have to sort of add like an extra 180 degrees to the player's position here. Let's come in here. So the add baddie function here. So you see there's a load of different stuff here. So definitely check out the baddie code here. So there's two different collisions here. There's one for the gumbos bumping into themselves, and then there's also a collision cube for them hitting everything else. So the one we're interested in is the move baddie here. So what this does here, so one thing to note is they have access to the level manager, and let's double check there. Add some. Oh, I think it's where is it? Where is it? The baddie manager update. Yeah, the update function itself, you pass in the player's position, and that basically allows them to find you, basically, or rather look at you here. So they work out what your position is here. Notice that the X, Y, and Z is set up Z, Y, and X. And once you get that value back, we are adding 270 to it. The reason for it is the sine and cosine are off by 90 degrees to sort of align them up with a world, but then the direction needs to be 180 degrees to the actual player's position. So they end up facing in the opposite direction to you, basically, so that they can move in the opposite direction to yourself, which is what they do. So all of these, they use the move position, which takes in the yaw. So this basically moves a position down like an angle at a speed, and you can also have strafe on it. I've covered this function in some other videos here, so I'm not going to go over this here. Basically, you have to call it once for the moving on the x-axis down the y angle, then check for collisions, and then you do the same on the z-axis here and check for collisions here. So the first part here is if the baddie is on the ground. So rather than having like a whole stack of different states, it only really is is on ground or not. If it's on the ground, then obviously it can walk normally. Otherwise, you have to go through the is falling, is on the ground amount of functions here, and then check to see whether it's on a platform or whatever. So basically the whole sort of get angle and wrap angle gives you the homing code, if you like, for the enemies. So that's all I'm going to sort of go over here. So let's wrap this up with the lighting, and so let's go over the lighting first. So the lighting is new stuff I've added here in Scene 3D. So I've created a light type. So these light types, they basically contain the same properties as the grrlib diffuse lights. Let's find where they are. Here we go. So this is a GRR diffuse light. So there are a maximum of 8 that the Wii can have. I'm only using 1 in this game, but I've set up some. Let's close loads of this. So they take in a brightness value, which can be between 0 and 1, or a distance value, which is their sort of effect, I believe, and that can be between 1 and 20. And then there's a color value, and there's a boolean of whether it's switched on or not. And then I have a list of these lights. Like I said, there's 8 hardware lights that you can have on the Wii. And then there is a set ambient function now as well, which takes a brightness between 0 and 255. And then there's some various functions to hand over lights here. So the player, I believe there's a light in here. There we go. This takes in the player's position here. And you'll see that the when we add a light here, we add in a color. So this is why there's like a whitish sort of color to the first and third level. Well, it should be. Otherwise it adds in a kind of like green color here. You see that that's the red, that's the green, that's the blue. And although it takes the alpha isn't actually used, I don't believe. And then that light is updated each time the player moves. You see that it takes the player's Z position, and then the Y position, there's like a variable here which adds 100 to the player's Y position so that the light is directly above him, and then you can just call the set light position with the light's ID and its new position in the world. And that's how the lighting sort of works there. So the other thing to talk about here is the Skycube. So in the render function here, which I would recommend you take a look at, whenever we sort of draw a sky or something that should not be affected by the light, what we have to do is we have to switch all the lights off first. Then what this is doing here is it's drawing the sky. So at the start of the LevelManager render function here, we set up the sky to basically be in the same position basically as the player, except its Y position is 0, so that it always appears to sort of physically sort of move with the player, if you like. Obviously it's the background, so it should do that. And then there is also the water, which also tracks the player as well. As you see here, the lights are off, the sky box is drawn here. We then turn the water on, the lights on. Then we draw the water, and then we draw everything else. The water is literally where are we? Very long video, I think. So the water is using this mesh called Sprite Above, which is basically just a plane like I showed you earlier on in the video with its UV scaled 2:2. And the reason why it's scaled 2:2 is because there is a new function in the display manager code here called DL update, and you have to pass in the mesh ID and the model data again, and then you pass in the offset to the UVs on the X and Y position here. And then if I bring this up here, so this appears like it's creating it all again, which it kind of is. Except what it's doing now is when it's converting the UV positions here, it's adding the offset to the UX and UI position here, so it can kind of create the scroll. That's how that sort of works. Again, have a play around with this to get a feel for it. in the level manager here. I think at the bottom here, where is it? I think it's in the level manager update code. Nope, it's in here. So you'll see here we update the scrolling code here. So if the scroll value is less than -1, then we set it back to 0. And then we basically pass in 0 for the X scroll of the water and 1 scroll Y here for that, and then reset that timer there. So that's basically it for this video. Hopefully it's not been too rambly. Again, there's a lot of different topics to cover in here. Yeah, let me know how this went. And that's it for my Wii videos. Hopefully they've been useful to you, and hopefully this one will allow you to create a full game. I will add the Blender file and the level files to the downloadable project. So that's it for this video. Thanks for watching.